All right. Okay. Well, nice to see everybody. Hope you had a nice weekend. The plan for today is to finish up a couple more examples with proof by contrapositive, which we started last week, and then start some examples talking about proof by contradiction today, and then we'll wrap that up on Wednesday. So any questions before we get started today? Okay, so at the moment, I'm looking at worksheet 7. So this is the contrapositive proof one. So we started this last time, and by my recollection, partly together, partly in groups, we proved the first 3 statements on this worksheet. And I don't think we got to the last 3 statements. So let's pick number 5. And so just recall a couple of general things. Let me get a fresh piece of screen. So when we're doing kind of our proof techniques that we have so far, and this would be if we're trying to prove if P then Q types of statements. We've talked about direct proof. Which is suppose P is true, ... Therefore, Q is true. That's kind of the most natural way that you probably would think about trying to prove something. And what we talked about last time was another method called contrapositive proof. And how this goes is that a conditional statement is logically equivalent to its contrapositive. Which would be not P implies not Q. So when we do contrapositive proof, we start by supposing that not Q is true, and hopefully we work our way and get to the point that not P is true. And if we can show that is true, then it's equivalent to showing the original implication is true. So this is a good technique to do when I would say it's probably preferred that you try and do direct proof, but sometimes that initial step might be hard to get going with, in which case maybe supposing not Q is true sometimes might be more advantageous. But any general questions about those techniques? Okay, so then the problem I want to start with was that number 5. And the statement here is if 3 divides x squared, then 3 divides x. So if we're proving this by contrapositive, and so we've been talking about when we're writing proofs, like what should we do for the last line? Do we need to say like therefore by contrapositive blah 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 is true? So I think it might be useful when you're going about your proof technique to just indicate like what method are you using from the get-go. Then the reader is going to know what kind of logic you're trying to employ to prove this. So if I'm going to prove this by contrapositive, what would be the start for this proof?
Would that be suppose 3 does not divide x?
Yeah, so we start with, here's our kind of Q, and here's our P. So we start by assuming not Q. So let's suppose that 3 does not divide X. And okay, then we can try and think of, well, what does that mean? And so really what this is implying is then that would imply that when we do try and divide X by 3, we get a remainder. So, okay, that means this number X, shouldn't start my sentence with a symbol. So we could say, therefore, so one way that we could restate what it means to not have 3 as a divisor means that when we divide X by 3, we have a remainder. So in other words, we can write this number X as 3 times a constant with a remainder, which in this case would be either 1 or 2. So supposing that 3 is not a divisor of X, therefore it is logically equivalent to saying that statement there. Any questions about that? So any thoughts about what we can do with that observation?
What is H?
Some integer. I just didn't want to use the same letter here and here. So it's just representing the integer that could go in this place. So I know that X either has to look like this or it has to look like that. What might be a good strategy to try next? If I know that either X looks like this or X looks like that.
Could do cases.
Sorry, I think I heard that.
You could do cases.
Yeah, so we can try cases, right? Because now we just have 2 of them. If we were thinking about a divisor of 7, okay, that would be a little bit annoying to have to go through all of those cases. So this gives us 2 cases. Say case 1, if X is equal to 3K plus 1, then remember, like, what it is that we're hoping to get to at the end is we're hoping to say, well, therefore not P is true. And that's what we're hoping to show in the end by proof by contrapositive. So if I'm over here trying to show something about whether or not 3 divides X squared, what might be a good thing to do next?
Square X.
Square. Sure. X squared would be 3K plus 1 squared. And expanding that out. Gives us that X squared is 9K squared plus 6K plus 1. Then what do you think we can do with this in order to show that X squared is not divisible by 3?
Replace it with K.
Replace it with K? What do you
We
mean by
wanna
that?
try and factor 3 out?
Yeah, so we can use the same sort of idea that if we want to show that x squared is not divisible by 3, then it's sufficient to show that it can be written like 3k plus 1 or 3h plus 2. If we can write it in that form, that would imply that we have, when we try and divide by 3, we're going to have a remainder of 1 or 2, which would mean not divisible by 3. So, right, so what can I do with this expression for x squared that we have to try and show that it is going to have to appear to be in a form like this or in a form like this, right? What we're hoping to show is that if this is true about x, the same can be said about x squared. Okay, so I've got a sheet here.
If you
This says,
if you
your
just try to
name-
factor a 3 out of the polynomial, you'll see that you can't
Yeah,
divide the third term by 3.
that's right. So we can start to try and put it in that form. I just want to point out, I have a list here of your names that I just totally randomly generated here. So I will start calling on people. It's not at all to put people on the spot. I'm not my intention. I just want to make sure that I hear from everybody in the class. So if I call on you, not picking on you. If you're not sure, you can say, I'm not sure. I just want to give you all a chance to talk. Okay, so I think, John, do you mind just explaining what you were saying? I think that was you.
Yeah, I was just trying to say, if we try to factor a 3 out of k squared, we see we can't divide the third term by 3.
Okay, so the third term is not divisible by 3. So maybe let's think about what would go in the blank here. I want to take this thing, 9k squared plus 6k plus 1, and write it as 3 times something plus 1. Or hopefully that something is an integer. So doing the algebra inside here, right, we would have a 3k squared and 2k. So I could factor out a 3 from the first 2 terms. So now I've written it as 3 times some integer plus 1. So that would tell us that 3 is not a divisor of x squared. Any questions? Okay, so I'd like you guys to just try walking through the second case and see if you can get a similar result. So the second case would be that this x is actually 3 times some integer plus 2. And again, I'd like to then show how we can get to that point, and if we can show that for both of those cases, then we're done. So, does anybody want to volunteer to, you don't have to have the full proof, but to try and narrate us through this part? Okay, Zara, do you mind, what do you think might be a good next step if you're there? Ah, perfect, yes. So just to back up for a second for everybody. So we did case 1, which was saying it's not divisible by 3 because we have a remainder of 1. And then we want to show that if x is not divisible by 3, then x squared was not divisible by 3. So now we're going to take this other case. It's also possible that x could have a remainder of 2 when we divide by 3. But if that's the case, we still want to try and show the same thing, that x squared is not divisible by 3. So if I've got a setup for x, what might be a good next thing to try and do? Do you have any thoughts, Zara?
Show that this is not divisible.
Yeah.
Okay, by 3. Sorry, I want to have more time.
Okay, that's fine, no problem. Anybody else want to have a suggestion?
I'm still working through it, but I can try.
Sure, go ahead, Basi.
So I said that if x is equal to 3h plus 2, then we have x squared is equal to 3h plus 2 squared.
Okay.
And then I said, which gives x squared is equal to 9h squared plus 12h plus 4. I did my math right.
Okay, so far that looks good. So we're taking the same sort of idea. If we know what x looks like, let's then use that to figure out what x squared looks like. And so we've got this.
Nope.
Yeah,
I was just gonna keep going. Do you want me
yeah,
to?
please, go
Okay.
ahead.
So then I pulled, I knew that I needed to pull a 3 out somehow, so I divided that 4 into 3 plus 1.
Okay. So like that. Mhm.
And then I pulled the 3 out of that 9h squared plus 9h plus 3. I mean 12h.
Good. So that means we've got x squared is equal to 3 times 3h squared plus 4h plus 1 plus 1.
And I just assumed that because it's in that form that we originally had, we can prove that it's not divisible by, or 3 is not divisible by x squared.
That's right. Yeah.
But
Now it looks like this, which means it's not divisible
Mhm.
by 3. Yep. Yeah, and so from here, that's right. It's a similar idea. So since 3h squared plus 4h plus 1 is an integer, we have that x squared is equal to 3 times a plus 1 for some integer a.
I have a question.
Yep.
So if I didn't take a 3 out of that 4, and I just left it as if there was a remainder of 4, I guess that doesn't really make sense, does it?
Yeah, so you can't have, it's not possible to have a remainder of 4 when you're dividing by 3, right? So you just want to make sure that your remainder should be something less than 3, but not 0. So,
Yeah.
so yeah, so that's why you kind of need to take that 4 and just say, well, 3 of it would get sucked up into the divisor, and that just leaves that extra remainder of 1. Yeah. And so that does it, right? So we've showed that, okay, if x is not divisible by 3, that's equivalent to saying it has to look like this, or it has to look like this. If it looks like this, then we know that x squared is not divisible by 3. If it looks like this, then we also, again, know that x squared is not divisible by 3. So therefore, we just showed that if x is not divisible by 3, x squared is not divisible by 3. So the contrapositive, if x squared is divisible by 3, that therefore implies x is divisible by 3. So at this point, if you're writing up your proof, at some point, it's nice to tell the reader like what you're doing. You can either say that at the start, or you could say it at the end, like therefore by contrapositive, we've got this result. And I think out of the two, it's probably nice to let your reader know what you're doing from the get-go as opposed to at the very end. Any questions?
I have one, sir.
Yep.
Why do I feel like sometimes this proof isn't as general as some of the proofs and the generality that's required for other proofs?
Yeah, I mean, I'll say, first of all, there are different ways of proving the same statement. So there may be a better way of proving this, certainly. I'll say like cases tends to be a kind of awkward proof technique. And so sometimes it's nice to try and avoid it if you can. Sometimes it's unavoidable. So I would say there's usually more than one way to try and prove these things. And you might want to think to yourself, like, what is a good proof seem like to me? Have I written this the best way? And I think you're right. This isn't the nicest thing that we've written, but logically it's correct. I don't think there's anything wrong in it logically, but then you can look at this and say, like, this seems like maybe this wasn't the most direct way. Would direct proof work here? How would I start if I had direct proof? And just recall that if you were trying to do this by direct proof, that would mean you would suppose 3 divides x squared. So that would tell me that x squared is equal to 3 times k. And it's like, you know, here's kind of where you sort of hit a dead end if you're trying to say something about x, because now you want to take square roots, and that's not as nice of a thing to do as opposed to taking something that we know and squaring it. So I think that's kind of the issue with trying to do this directly, is that we don't know how to simplify square roots, whereas we do know how to simplify squaring expressions. So yeah, it's maybe not the most elegant thing, but it works. And I think it works better than direct proof here because we wouldn't know what to do with that expression x squared is 3k. But I think that's totally, yeah.
Is there any other way to do it, or this is like the only way?
So far we've got direct proof and contrapositive proof, and we'll talk about contradiction. Out of those two methods that we've talked about so far, direct proof wouldn't necessarily work. We seem to have hit a dead end at this point, whereas contrapositive proof was able to work. So out of those two possibilities, this is better than the direct proof because the direct proof kind of just stalled out. There may be other proof techniques that we'll get into that might be better, sure. But I think for now, we just have 2 types to choose from, and out of those 2 types, direct proof doesn't work, but contrapositive does work.
Awesome, thank you.
Okay. Anything else about this one? Okay, so let's see. So working on the same worksheet, let's take a look at, let's do question number 4, which deals with power sets. So statement 4 was if power set of A is not a subset of the power set of B, then A is not a subset of B. And so I hope it's pretty clear what this sort of, maybe it's not, what this notation means. So when we put these slashes through, it just means not in mathematics, not equal, not whatever. So in this case, we put the slash through the subset symbol, it means not a subset. And, you know, if we're kind of thinking about proving this, again, we've got two methods that we've been discussing. We've got the direct proof method, which would say, well, let's suppose that the power set of A is not a subset of the power set of B. Then you would have to go from there. So for example, you could say, okay, there's some element in the power set of A which is not in the power set of B, and so on. If we're trying to prove this, as I'm suggesting, to try contrapositive, then we start off by supposing the negation of the conclusion. So we're going to suppose that A is a subset of B. Okay. So what that means is right, any element of A is therefore going to have to be an element of B. And again, if we're going to do proof by contrapositive, then what we're going to hope to show is the negation of the hypothesis. We're going to hope to show that therefore the power set of A is a subset of the power set of B. So any questions about how we got the first or last sentence of this proof? Okay, now is the hard part, right, is filling in the space between those. So again, if we want to prove that the power set of A is a subset of the power set of B, then I need to show that any element in the power set of A, and remember, the elements of power sets are sets themselves. So that means if I have some set Y, which is in the power set of A, we would like to show that it has to imply that Y is also in the power set of B. So I'm just kind of doing some scratch work with definitions at the bottom, and then what it means for Y to be in the power set of A. What does that mean? How would Y be related to A if it's in its power set?
All the elements of Y are also in A. So
Yeah.
it's a
So it's a subset, that's right. So we're trying to show that if Y is a subset of A, that has to imply, therefore, that Y is a subset, of B. So we just want to kind of clean up this. But I think sometimes if you get to this point and you're like, okay, I just exhausted the information that I know. I know X is in A, then X has to be in B. Great, what am I supposed to do with this? Well, you can do a lot of things with it. It depends on what it is that you're trying to show. And so we're trying to show this, and then you might think to yourself, well, how would I show that? I would need to show that any element in the first one is in the second one. And then it's like, what the heck is the power set? Okay, that's what it means to be an element in the power set. So we're kind of just unpacking this. So this part over here just comes from a definition of subset. And this part over here comes from thinking about the definition of a power set. So we kind of want to invert this. We're going to kind of first think about this, and then think about that, and then try and get to that conclusion. Is how I'm thinking about it now. Okay, so great. So let's then consider some element in the power set of A. Okay, and again, the goal here is we want to show that for any arbitrary element in the power set of A, that has to be an element in the power set of B, and then we're done. So let's consider Y in the power set of A. Okay, then by definition, we know that Y, right, is a subset of A. So then let's consider any element in this subset Y. Okay, and so since we know that this element Y is in the set Y, which is a subset of A, then we know that lowercase y has to be an element in A. And then since we suppose since our assumption was that A was a subset of B, now that I have that every element Y is in A, therefore every element in Y should also be in B. So that by definition tells us that Y is a subset of B. Okay, and therefore the power set, well, I guess if Y is a subset of B, then it's an element of the power set of B. And that's enough to claim that we have power set of A being a subset of B. That's what we would need to do if we're doing proof by contrapositive. So all this stuff over here was just some scratch work. Okay, are there any questions?
So then would we have to put like a conclusion since that was contrapositive, like basically take it back to the original statement?
I would say if you haven't indicated already that you're doing proof by contrapositive, then you should. If you've already told the reader, I'm proving this by contrapositive, then you're good to go.
Okay.
Yeah, you don't need to state it twice. And I'm suggesting that it's nice for the reader if you just state it from the get-go, I think, then they can pick up on what's going on. So if you explain, I'm doing proof by contrapositive, and you've shown that, then it's for the reader to therefore say, okay, this is equivalent to the contrapositive of that. So yeah, the shorter answer is you could just stop right there if you already told the reader you're doing proof by contrapositive. Okay, any other questions? Okay, so let's see, as far as this sheet goes then, we did this one just now, and we did this one. We haven't done this one yet. I'll leave that for you guys to get some practice on it, and I'll put up a solution to it with these notes. But I'll leave that as an exercise for you to work on your own. It is an if and only if statement. So maybe I'll just motivate how you might want to start something like that and leave the details for you to think about. But in 6, it's saying that the set A minus B is equal to the empty set if and only if, sorry, I got lazy. A is a subset of B. That doesn't look right. So am I missing a? Do I have this right? That doesn't look right. I see. Yes, that is correct. Okay. Yes. So this is the statement that we're trying to prove. Sorry. And so this is an if and only if. So this means you need to prove both directions, right? So you would need to show A minus B equals the empty set implies that A is a subset of B. And then you would also need to show the other way, that if A is a subset of B, that implies A minus B is equal to the empty set. And so if you're doing both of these by contrapositive, which is what I might suggest to you, then in proving this first one, you would start by supposing the negation of that. So if we're doing this by contradiction, you would say, well, let's suppose A is not a subset of B. And therefore, the negation of the original hypothesis is true. So that's how you would prove this direction with contrapositive. And if we were trying to prove the other direction also using contrapositive, then that one would start with suppose A minus B is not equal to this. And therefore, you get the negation of the original hypothesis. So you have kind of two contrapositive proofs that you would need to do here. They both are very similar to each other, and they're both easier than the power set thing that we did. So I think the power set proofs tend to be the trickiest because power sets are tricky themselves. All right, questions? Okay, then let's start discussing a bit about proof by contradiction, which is what you read a little bit about or watched before class today. So this is in chapter 6 of the textbook, if you're following along there. So the front page of this worksheet is basically the short version of what you looked over for the quiz. And so how proof by contradiction works is we start by supposing, so basically what we're going to show is that if the negation of our statement is false, that would imply that the original statement is true. So rather than prove that P is true, we're going to prove that not P is false. And how do you prove that something is false? You can prove something is false by showing that it leads to a contradiction. So the general outline for a proof by contradiction, again, the idea here is we're hoping to show that the negation of P is false, which is going to therefore tell us P is true. So that's the real goal, is we're hoping to show that P is true, but we're going to do that by showing that its negation is false. So when we're doing proof by contradiction, our first step is going to be, let's suppose the statement that we're trying to prove, let's suppose the negation of that statement is true. And then show that if we assume the negation is true, that's going to get some contradiction. Therefore, our original assumption that the negation is true must be wrong. That statement is false. So let me skip over that part, this stuff for now. So this was one that that I started talking about in the video. So let's say we've got this statement, the square root of 2 is irrational. And we're going to work with the following definitions for rational and irrational numbers up here. So basically just define an irrational number by saying it's any number which is not rational. So question 2 is asking us to try and show that square root of 2 is irrational. Okay, this is not a conditional statement at all. There's no if, then. There's just one statement. Square root of 2 is irrational. So since this is not a conditional statement, we think about, okay, let's say we wanted to try and do this by direct proof. Right? We can't do that because we can't suppose the thing that they're asking us to prove. And there's no if then here. So there's not even a clear way to see how I could use direct proof. This is not even a conditional statement. So we can't use direct proof for the same reason contrapositive proof is not going to work. So if we're not dealing with a conditional statement, then there's really no way to apply the direct or contrapositive proof. So let's try proof by contradiction. And so proof by contradiction is always going to be by let's suppose that the negation of our statement is true. So in other words, let's suppose square root of 2 is rational. And then we're going to try and get some, if we assume this, that there's going to be some logical contradiction that comes out of this, and therefore our original assumption must have been wrong. So we're going to start here. And so if the square root of 2 is rational, then there exists 2 integers . Okay, which basically says we can write the square root of 2 as a ratio of 2 integers. And the denominator is non-zero. that's basically just writing out what the definition of rational means. So we're going to also assume here, without losing any logic, that this, we've got square root of 2 written in its reduced form. So in other words, A and B don't have any common divisors besides 1. Okay, so we're going to say the only common divisors they have would be a plus or a minus 1. Okay, any questions so far? Okay, so then if I square both sides of that equation, then that would give me that 2 is equal to a squared over b squared. So in other words, 2b squared is equal to a squared. And if we know that a squared is equal to 2b squared, then what type of number does a squared have to be?
That should be a factor.
Even.
Of 2.
Yeah, so then we know that a squared is even. If a squared is even, what does that tell me about a?
It's also even.
How do you know that?
I think it was in the book.
I
We
think
did
that was
this
in the
last
example
time.
approved.
Yeah, so we proved this last time. And so let's see, this was on, I think, the last worksheet that we just did. I think that one was 6. I'm trying to remember my worksheets. Let's see. Sorry, I think that was worksheet 7, something like that. Okay, so this tells us that a is even as well if x squared is. And the point I want to make here is we don't have to reprove things that we've already proven together. So I don't need to go through this proof again, but you do need to state where we proved it. So if it's a theorem in the book, then you can say from theorems, etc. in the textbook. If we proved it together in class, then you can say exactly what I did. From this worksheet, this problem, we've already proven this. Any questions? Okay.
Isn't it also just true because the left side has a 2 in it and any number times an even number is another even?
The left side has a 2 in it. That tells me that by definition, okay, so you just want to be, yeah, like it's equivalent saying if a is even, a squared is even, or if a squared is even, then a has to be even. These are interchangeably statements. So you're kind of making a couple of observations in one, but you just want to be a little bit careful. We don't get that A is even directly from this. We get A squared is even from this because we can see A squared is 2 times something. So there's kind of a 2-step process here. This tells me that A squared is even, and then we have this theorem that then therefore tells me that A also has to be even. So yeah, I think you want to map that out in 2 different things because using the definition of what it means to be even, this wouldn't tell me that A is even. It tells me A squared is even. Okay, any other questions? Okay, so then, so since A is even, we have that A can be written as 2 times some integer. Let's use a letter we haven't used. I don't think we've used K yet. Okay, and again, when we're doing proof by contradiction, not even sure where I'm going right now, right? I can go, I want to get to a contradiction. I don't want to, not any specific contradiction, any contradiction will do. I haven't gotten there yet. There's nothing that I've said so far that contradicts anything about the square root of 2 being rational. But let's use this back over here. Let's plug it into this identity that we had over here. So if A were even, then that means we've got 2b squared is equal to 4k squared for some integer k. And so if we divide both sides of that equation by 2, we have b squared is equal to 2k squared. So now we basically have a contradiction here. Does anybody see what that contradiction is?
We've basically grown an extra 2.
Sorry?
We've basically grown an extra 2 in our equation.
What do you mean by that?
Well, we knew that 2b squared equaled a squared, and in the process of proving a was even, plugging it back in, we now have b squared is equal to 2k squared instead of, it should be b squared is equal to 2k squared over 2.
That's right. So we've got this 2, yeah, so we got an extra 2. That 2 is on the right side. That's right. And so we're trying to get a conclusion here. I think we've got it. So I know that b squared is equal to 2k squared. So what do we know about b, or b squared for that matter?
So b squared is also even, and we said a little bit earlier that a and b don't share any common divisors other than 1.
Yep, perfect. That's right. So this tells us right now that b squared is even, right? That I can claim so far. Okay, and so I don't need to restate the same theorem, but we can say that, okay, therefore b squared is even by the same logic that we just explained for a, we get that b is even. And so if a and b are both even, then we know that 2 divides a, and 2 is a divisor for b. And I'm just going to highlight this part. You don't necessarily need to do this on your work, but here we've got that 2 divides a and 2 divides b. And over here, we made this assumption that we've just written square root of 2 in its lowest form. And so A and B don't have any common divisors other than 1 or -1. And so here's our contradiction. So therefore, our original assumption is false. And therefore, if the original assumption is false, then we've shown that square root of 2 is irrational. Okay, any questions about how we got that contradiction? So that it's a more open process, I'll say, than the other proof techniques in the sense that the goal is just very generally to get a contradiction. Any contradiction will work. When we're doing direct proof by contrapositive, we have a very clear goal that we want to get to. So that's one thing that's a little bit tricky about contradiction is kind of understanding what is the contradiction that I'm trying to get to in the end. And sometimes that won't play itself out until you just start trying different things. Okay. So that is generally what proof by contradiction looks like. So here we applied this on a statement which was not even a conditional statement, but like most of the other statements that we're working with, most of the time in mathematics, we are trying to prove conditional statements. So let's think about how we can apply this method of contradiction to prove conditional statements. And to just kind of back up for a second, when we negate a conditional statement, so I just put this up here, since when you're doing proof by contradiction, the very first step is to suppose the negation of the thing you're trying to prove. So it just might be helpful to review how you negate statements. If we're trying to prove a conditional statement by contradiction, then the way that we negate an implication is by assuming the hypothesis is true and the contradiction is false. That's the only way the conditional statement is wrong. So when you're proving an implication using contradiction, proof by contradiction, then your first step is going to be, let's assume P is true and Q is not true. And then there's really no goal in the end other than to show that somewhere along the way that leads to a contradiction. So let's work with sticking with the rational and irrational theme. Let's go through the first one over here. And then I think it would be good practice for you to try and do the third one is pretty similar to that one. So here we've got a conditional statement. We're going to try and prove using proof by contradiction. Okay, and so, so here we're trying to show if X is rational and Y is irrational, then the sum X plus Y is irrational. And so again, if you're ever having some trouble with these, we will definitely give you some partial credit for trying to show work about how you tried to access this problem. So if you're ever stuck on these, never hurts to just try and state what these statements are. And Q is the sum x plus y is irrational. And so let's do this proof by contradiction. Which says, let's suppose the negation of this conditional statement. And again, the negation of this statement would mean that there is some rational number x and irrational number y, that their sum actually winds up being rational. That would be the negation of this statement. So we've got, we're going to suppose that P is true, which is X is rational, Y is irrational, and that Q is not true. So now Q not being true would be that the sum X plus Y is also rational. Well, I guess is rational. Okay. So if I know that X is rational, then what can I say about X?
It's equal to some integer A over some integer B.
Okay, and we need to stipulate one additional thing here, right? Which is what? What should be true about B?
B doesn't equal 0.
Yes, thank you. That's right. So, or else this wouldn't be defined. And oftentimes that is like a really, really important observation to make. So yes, so then we know that X is equal to A over B for two integers A and B, where B is not 0. And we can say something similar about the sum X plus Y. For two integers C and D, with the denominator of that one also not being 0.
For X, do we want to say that they don't have common divisors like you did for the previous one, or is that not relevant here?
It's not going to make a difference here.
Okay.
So yeah, we don't need to state that here. It was useful in the previous problem because we wanted to get some contradiction, and the only way that I could think about doing that was assuming that they were reduced and then showing that they had to share a divisor. So here, I don't think it's going to make a difference, hopefully, whether or not we have these things reduced. So we've written out our assumptions. X is A over B, and X plus Y is C over D. Anyone have any ideas about what we can do with this? So we want to say something about Y, right? We want to show that Y, well, we want to get some sort of contradiction here. And so one thing that we've claimed about Y so far is that it's irrational. And so if we can somehow say, if we assume this first statement, this is going to imply somehow that Y is rational and irrational at the same time, we've got a contradiction. So if I have an expression for x plus y, and I have some expression for x, what might be a reasonable thing to do with those two expressions?
I'm going to replace y with a rational
Yeah, we can try and show that
or
y
an
is,
irrational number, such as let y equal √2.
yeah, well, so let me just put this note up here. If we can show then that would be a contradiction to this statement over here, right? Our original assumption. Anyone have any ideas how we might be able to show that y is a rational number?
You can move x to another side. Yeah, like y equals c c over d plus a over b.
Yeah, exactly. That's right. So I can take these two things and say, okay, well, what would happen if I took x plus y, not minus, right? X plus y minus x would give me y. So I can say, okay, y, which is equal to x plus y minus x, is equal to, well, we knew that x plus y was c over d. And then we knew that x was a over b. So subtracting those two together gives us something which is equivalent to y. And we can do some algebra over here and get that this is bc minus ad all over b times d. So I have an expression for x plus y. I have an expression for x. So we're just trying to do the algebraic thing and say, well, then therefore, what would that imply about y? And so why is this a contradiction over here?
That's a rational number.
But and how do we know that this is rational?
Because B, C, A, and D are all integers. So when you subtract them, you have an integer over an integer.
Yep. So we got BC minus AD. That's going to be an integer. And BD is an integer. But there's something else we need to say here, right?
It's not equal to 0.
But it's not equal to 0, right? And if we didn't have this assumption at the start about B not being 0 and D not being 0, we might have some problems. But again, this fraction needs to be defined, so it can't have a 0 in the denominator. Sorry, that's 2 D's. Okay, and we know that that is not going to be 0 since we know that both B is not equal to 0 and B was not equal to 0. Okay, so that tells us y is a rational number since it can be written as a fraction of two integers. And that's our contradiction, right? Since over here, we just reached the conclusion that y is rational, but we assumed from the get-go that y is irrational. So you could stop it at that point if you stipulated that you're doing proof by contradiction. But I think sometimes might be nice to just say, therefore, that if we have a rational number x and an irrational number y, their sum has to be irrational. And that wraps up that proof. So that's how it works for doing contradiction with a conditional statement. Any questions about that?
Did we not show not P in that last statement?
So remember here, what we're trying to show is that we have some contradiction. So we're not doing contrapositive proof. With contrapositive proof, you show if not Q, then not P, and you're done. But we're proving this by contradiction. So we haven't supposed not Q is true. We've supposed two things, that P is true and not Q is true. And with those assumptions, what we're hoping to get is any contradiction would work. So I think what you might be thinking about is how you would prove this using contrapositive. So with contrapositive, you would assume that not Q is true and try and show that not P is true. So I'll say that proof by contradiction is actually like one of the most powerful proof techniques out there. It's maybe a little bit trickier to get your feet wet with it because there's oftentimes no clear-cut goal other than I want to get a contradiction, which is much vaguer than saying like, this is the end of my proof. I know this is the last sentence. So with proof by contradiction, you're just trying to work towards some crazy contradiction somewhere. So the it's not as clear, like, you know, what you're looking for as opposed to with direct proof or proof by contrapositive. So we'll practice more of these on Wednesday. What I would suggest to you is to give this one practice on your own. I'm not planning to go through it in class on Wednesday. So give that one a chance as a good practice. And if you have any questions about it, I'm happy to talk about it at the start of class. If you don't have any questions about it, then we'll start with going through 4, 5, and 6. And then we'll start talking a little bit about how we can now start to do some proofs with kind of more sophisticated mathematical objects like functions, and showing that functions are injective or surjective and things like this. So we're gonna start to take these proof techniques and apply them to functions, and we'll start to do some real analysis with them. So you'll get some hint at some of the things that you'll be looking at in Math 4310 if you're planning to take that eventually. If you're a math major, you definitely should be planning to take that. You have to. Okay, so I will stop here for the day. No homework is due tonight. You've got your homework assignment that's due next Monday, but we will have a short reading quiz due before Wednesday's class. So if you have any questions, welcome to stick around. Otherwise, thanks everyone. Nice to see you all, and I'll see you guys on Wednesday.
Thank you.
Thank you.
Thank you.
You're welcome.
Thank you.